Unit 6, Chemical Equilibrium. This is absolutely my most favorite unit. It's difficult, it's challenging, but it really is not as hard as it seems. I think a lot of times we're scared by the word equilibrium. All that equilibrium means is it means that the reaction starts, and as the reaction starts, the products start to form. And as the products start to form, the reaction starts to go backwards. And as the reaction starts to go backwards, you get eventually to a state where the forward reaction and the reverse reaction are occurring at the same rate. And when that happens, that's when you've reached equilibrium. Typically, when you get to equilibrium, it looks like, from our point of view, it looks like the reaction has stopped. Okay, because we can't see anything happening. But all that means is that the reaction, the forward reaction, is still going at the same rate. The rate of the forward reaction is equal to the rate of the reverse or the backwards reaction. Okay, which means that usually, again, when a chemical reaction starts, here we can kind of see this. So this would be the concentration of the reactants. So reactants. Okay, and down here would be the products. So initially there's no products, and what happens with the reactants as the reaction begins is, of course, the concentration of the reactants goes down. And because the reactants are being used up to make the products. Okay, but as that happens, that the amount of the products obviously goes up. And eventually you get to a point where they basically stay flat. And again, it looks like from our point of view that the reaction is happening, but now at this point we have reached equilibrium, which again, remember what that means is that the rate of the forward reaction and the rate of the reverse reaction are equal to each other. Equilibrium does not mean that you have the same amount of reactants as you have products. It doesn't mean you started with 1 molar reactants and now you have 0.5 molar of both. Equilibrium does not mean that. All that equilibrium means is, it again, from our point of view, it looks like the reaction has stopped, which means the concentrations are going to remain the same. But what it really means is that the rates of the forward and the reverse reaction are now equal to each other. Clearly, at the very beginning of the reaction, the rate of the forward reaction is going to be fast, and the rate of the reverse reaction is going to be 0 because there is no products, okay, or there are no products. Okay, but eventually the speed or the rate of the forward reaction is going to start to slow down, and the rate of the reverse reaction is going to start to speed up, and eventually you're going to get to a point where those two are going to equal each other. And when they do equal each other, again, now you are at equilibrium. And you may, but probably not, but technically you could have the same amount of reactants and products, but usually you don't. Okay, and we're going to see that here in probably our next video. Okay, but the rates of the forward and the reverse reaction are the same as when equilibrium has been established. Okay, some of this other stuff, it looks like it's stopped. Sometimes, so what you'll see a lot of times, if there's colors involved, is you will see a combination of the two colors. For example, this cobalt compound has a red color associated with it. This cobalt compound has a blue color associated with it. So when you reach equilibrium, what you're gonna start with the red component, and then you're gonna see it slowly transition to what's going to look like a purple color, because now you've got both the reactants and the products present in that solution. They're going, notice our equilibrium arrow here going forwards and backwards, representing the reaction going in both directions. Okay, so here's an example question that you could see involving this. It says equimolar amounts of Cl2 and O2. So that means you're starting with an equal amount of Cl2 and O2. And right away you're going to notice, well, wait a minute, if we start with equimolar amounts, doesn't that mean we're going to run out of chlorine first? If this reaction went, forget this, if this reaction went all the way to the right, doesn't that mean right away that chlorine is the limiting reactant? Absolutely yes. That's a great observation to make there. In this case, it doesn't really matter. But again, when they say equimolar, it means you're starting with the equal number of moles, and for every 1 mole of these that react, 2 moles of chlorine are going to react. Of course, chlorine is going to run out first. So you've got an equal amount of chlorine and oxygen injected into an evacuated rigid container. They react according to the equation below. And then you've got some pressures in the container. And they're monitored at a constant temperature and recorded in the table below, so the temperature is not going to change. So notice initially, again, here are our equal number of moles with, again, if the moles are the same and the volume and the temperature and the gas constant are the same, then of course the pressures are also going to be the same. So equimolars means equal pressures. There is no product at the beginning. And then notice that what happens over time is, notice that again, because of that 2 chlorines and 1 oxygen, for every 0.04 this goes down, this one has to go down by twice as much. And again, if this reaction were to continue in the forward direction, the chlorine would obviously run out first. And again, you can see that here. Every time the O2 goes down by an amount, the Cl2 goes down by double that amount. Okay, and notice that eventually, and you kind of start to see it here, and then you see it a little bit more here, and then you really start to see it right down here, is that eventually you get to a point where that forward reaction basically looks like it stops. And it looks like the reverse reaction, again, the amount of Cl2O also reaches an amount that doesn't change. And again, does that mean that the reaction has stopped? Nope. It just means that the rate of this reaction, the rate in that direction, and the rate in this direction are equal to each other. Remember how when we dealt with rate laws, when we had to use the previous step because there was an intermediate in there, and we would set the two sides equal to each other because the rates were equal to each other. And so we could, and that's what equilibrium means, is it means those rates are equal to each other. So here we can see that it looks like at right about this point right here, right about time 7, we have now actually reached equilibrium. So question A says, at time 4, so before we've reached equilibrium, is the rate of the reverse reaction greater than, less than, or equal to the rate of the forward reaction? Justify your choice. Okay, and we can see that at time 4, what's still happening here? Okay, at time 4, remember, at the very beginning, the forward reaction's going fast, the reverse reaction isn't happening at all. And slowly, you get to a point where they're going to equal each other. So the forward rate is going down, and the reverse reaction is speeding up until they reach equilibrium, and now they're equal to each other. So until you reach equilibrium, the forward reaction is going to go faster, and the reverse reaction is going to be slower. So at time 4, is the rate of the reverse reaction greater than, less than, or equal to the rate of the forward reaction? It absolutely is less than, and justify your choice, because the reaction is not yet at equilibrium. So the forward reaction is faster, or has a greater rate, however you want to say it is fine. Okay, is there a point where the reverse reaction is going to be greater than the forward reaction? There's not, no. Because once you reach equilibrium, now they're at the exact same rate. So that's where they would be. Once you reach equilibrium, that's when they're going to be equal to each other. But at this point, before you've reached equilibrium, the rate of the forward reaction is always going to be faster than the rate of the reverse reaction. You'll never get to a point where the reverse reaction is going to be greater than the forward reaction. Okay, so once you do reach equilibrium, now we're down here, the container holds fewer molecules of which gas? Chlorine or oxygen. So again, here's our chlorine, here's our oxygen. So this is how much we started with, and now at equilibrium, this is how much we have left. So again, pressure equals nRT over V. If oxygen has the greater pressure, and again, the volume, the temperature, and R is the same, the greater the pressure, the greater the number of moles. So at equilibrium, the container which holds fewer molecules of which gas is absolutely Cl2. Okay, and again, you can just say, because at equilibrium, that's 0.25, I'm sure it's atmospheres, yes, 0.25 atmospheres of Cl2 and 0.38 atmospheres of O2. And again, that's not the only way you can explain it, but simply by looking at the data table. And again, don't let this whole equal mole, well, there's equal moles that when you started, so at equilibrium they must be equal. No, we know that for every 2 of these, only one of those oxygens is going to react. So once you reach equilibrium, then absolutely the amount of Cl2 is absolutely lower than the amount of O2. Okay, and that is our introduction to equilibrium.